I think the name of the section is the equation AX equals B. Oh, the matrix equation AX equals B. All right. So A. So what we've done is we've taken a look at a system of linear equations, and then we tried to look at make a matrix, an augmented matrix out of it. And then we studied vectors in our last section. And so now we're just going to put those two ideas together and make a matrix equation where you have a matrix with being multiplied by vectors, and you're going to get another vector. So the boldface here, the boldface X and the boldface B is important to denote. And we have a matrix A, which is some M by N matrix. And then we can identify the column vectors A1 through AN. Remember, N is the number of columns and M is the number of rows. So an M by N matrix that's not augmented. An M by N matrix will have M rows, which is to say M equations, and N columns, which is also the number of unknowns. So if X is in Rn, then the product of A and X, is denoted by A times X, is a linear combination of the columns of A using the corresponding entries of X as weights. And so the X, if there's two of them, we could probably write XY, and if there's three of them, we could probably write XYZ, but we're going to assume that there are M or N, N of them, and that's going to be in Rn. Okay, how's that for starters? I have a couple of examples that I took from the textbook where they just want you to try to figure out what these things are equal to. So why don't we take a look at these two examples. Oops. And just go through the process of doing the matrix multiplication is essentially what's happening here. And so we're assuming that one of them is A and the other one's X. They're asking us to figure out what this is equal to. So according to the definition here, we're going to assume, let's group these things as A, A1, A2, A3, and these are vectors. And this will be X1, X2, and X3. According to this matrix multiplication should amount to X1 times A1 plus X2 times A2 plus X3 times A3. The bold are vectors in the typeset, and then so when I write them, I put an arrow on top. X has elements of A. No, A has elements of X. The A's here are bold. Is that what you're looking at? So the A's there are bold, and Oh, okay. So say your statement again. The elements of A, the matrix A, are all those lowercase a's, and the x vector is this vector that has x1 through xn. So when we say A and we write A as this matrix, the elements are columns, I guess. So what we're trying to do is we're trying to read these things. We're trying to read the matrix A as a set of column vectors that have been put together into a matrix. 1, 0 would be A1, and that's the first column of the matrix A. Yeah? You look at the whole column and treat this as if it was a column. So exactly how it's written here. Those numbers that you read out are all elements of A. But when you're reading in pairs, 1, 0 is the vector A1. 2, -5 is the vector A2. Each individual number in those vectors components are an element of the vectors. So this is your A1, your A2, your A3, and these are vectors. And this is your X1, your X2, and your X3. Okay? So we're not quite done here yet, because we can simplify this. This is a vector scalar multiplication and addition. So we can scalar multiply. And then we can add them to get our final result. Oh, you guys better check this. Yeah, I think it looks good. Does it look right? All right. So 3, 6 is your final result. So the product of the matrix A times the vector X in this case is going to be 3, 6. Okay? So now let's try this one. Why don't you guys try it? More than just the answer, I'm interested in the step where they're trying to describe this as a linear combination of those column vectors. Okay, is this what you guys got, more or less? What? Oh, because it's wrong. checking this, make sure you guys were pinged. 13. All right. Arithmetic. Oh, well, when you're copying stuff down, that could happen. So this is a this is a good example or good time to point out that there could be a lot of algebra mistakes, and I surely make my actually arithmetic mistakes when you're just adding, multiplying, subtracting, that kind of business. So when I ask you to really be careful about um, your work when you're going through this, especially when you're doing it by hand. Um, to after you write down a problem, check and double check again to make sure you wrote it down properly. And then at each step, after you do your calculations, do a quick check again to see if you did it correctly. Because if you go to the next step with an incorrect number, then the whole thing's going to be wrong. So just be careful. I suppose you could also use computers to check your work. MATLAB. If you can use MATLAB, go ahead and do that. Actually, you will have to use MATLAB, so might as well start practicing. Okay. Let's see. So now this is making the relationship between this new equation that we've come up with, and the vector equation and the systems that we're dealing with. So this is Theorem 3 in the textbook. If you have an n by n matrix with columns A1 through AN, and B is a vector in Rn, so it has n elements, that's the number of columns, remember, that you have in your matrix. Then the matrix equation AX equals B has the same solution, solving for x, the vector x, has the same solution as the vector equation A or x1 A1 plus x2 A2 plus all the way to xn AN is equal to B, which in turn has the same solution as the system of linear equations whose augmented matrix is the A1 through AN and then B. So this is the theorem that says that when we're solving for a system, we're actually solving for this, finding the weights for the linear combination, which is also solving for the equation AX equals B. So what we're doing here is we're kind of compactifying our notation for systems. You just write it as a matrix times some unknown vector with vectors with values that we have to find is equal to your B vector, which is the right-hand side of your system. Okay, let's take a look at the example that they have here. And so what I want to do first is, before jumping and trying to solve for this system or for this equation, maybe we can first try to figure out what the system looks like that corresponds to this particular matrix equation. So first of all, our x variable, I guess we should establish that our x vector has how many components in this case? 3. We match it with the number of columns. In this case, it's a 3 by 3, so that answer probably easier than thinking about it. But we would have our x vector, x1, x2, x3 would be what we were looking for. And in terms of linear combination, we sometimes call it C for the weights, C1, C2, C3. But we'll call it x1, x2, x3 in this case. And then you have your A matrix and your B vector. And so the system of linear equations should actually look like this. It would be the first row would be the coefficients of x1, x2, and x3 from your first equation. So 1x1 plus 2x2 plus 1x3 is equal to 0. That's the right-hand side, the first component of the right-hand side, or first component of your vector B. Second equation is minus 3x1 minus x2 plus 2x3. That's equal to 1. And then 0x1 plus 5x2. I could just say 5x2 plus 3x3 is equal to -1. So that's the system that you're essentially solving for in this matrix equation. Okay? So we want to find values x. So if we imagine making this matrix out of these two elements, a matrix and a vector, then we essentially have your augmented matrix. 1, 2, 1, and then augmented 0, minus 3, minus 1, 2, augmented 1, 0, 5, 3, and -1. And if you remember, if we have a matrix, an augmented matrix like this, we can just go through a row reduction to see if we can find a solution. So let's see, we have a 0 down in the bottom. That's good news. What can we do to the first equation and adding to the second equation to get rid of that -3? Yeah. So 3 times the first row added to the second. And then I usually put arrow R2, and that's the replacing the second row business, but it should be kind of clear that we're replacing row 2 here, so I won't do that anymore. And you have 1, 2, 1, 0, that stays the same. The -3 becomes 0 at the whole point in our move over here, elementary operation. So let's see, 2 times 3 is 6, 6 minus 1 is 5. 2 times 1 is, or 3 times 1 is 3, plus 2 is 5, and then 0 plus 1. And meanwhile, we didn't do anything with the last row, so that stays the same for now. And then I can multiply the second row by 1/5, but since the second row and the third row have matching 5s there, I can just get rid of this 5 first, and then I'll scale it down if we want to go to the reduced row echelon form. So let's say in my second row, I want to multiply the second row by -1 and then add it to my third row. So 1, 2, 1, 0 stays the same, 0, 5, 5, 1 stays the same. And now this one, I know I'll get a 0 down there. -5 plus 3 is -2, and -1 minus 1 is -2. Okay? Did I do my arithmetic correctly? All right, good. So now we know our pivot columns. We know that we have 3 pivot columns in the 3 by 3 matrix, A matrix. So we know that we are going to have a solution here. And we can take this to the row reduced form, reduced row echelon form, or we could just start solving from here. I think it's easy enough to start solving from here, going backwards, called the backward what they call it, back substitution or something. So I'll take that last equation over here that says 2x3, -2x3 is equal to -2, and this will give me a solution for x3. And then once you have that, you can just back solve. I have a 5x2 plus 5x3 is equal to 1, but x3 was equal to 1, so I'm going to go ahead and drop x3 in there. I have a 5x2 plus 5 equals 1, 5x2 equals 4, negative 4. And then x2, I get negative 4/5. So now plug all that stuff into the first equation. I have x1 plus 2 times x2 plus x3 is equal to 0. Let's see, x2 was this negative 4/5, and x3 was 1. So I'll figure all that stuff out. x1 is equal to, what is it? 3/5? Okay. Now, if you have MATLAB, or something that runs like MATLAB, should be able to get these things. MATLAB, by the way, is matrix lab. The math stands for matrix, not math. And that means this should work really well with matrices. So if we take a look at our augmented matrix here, we'll call it, I don't know, call it M. No, let's call it M over here. Equals to, and you'll see that there's going to be different ways of writing matrices, but I'll just do it like this for now. So that's the first row. The second row is -3, -1, 2, 1, and then the last row is 0, 5, 3, -1. So this is our matrix, and RREF is a command that does the row reduction for us. So if you look at this, this is in reduced row echelon form. We got ones and zeros, except for the last column, which is the set of answers, the solutions. So x3 is equal to 1, x2 is equal to negative 0.8, which, right? And then x1 is equal to positive 0.6. So I'm going to do more than encourage you to use MATLAB. Uh-oh. You have a worksheet where you have to either download FreeMat or Octave, which Octave is a program I was just using. Or if you have MATLAB, then that's great. You can use that. You can try to get MATLAB online. I don't know if there's any other ways, but I spoke about that in the first day of class, right? I have a discussion board there where you can find which program you want to download, and then I will have a worksheet available for you by the end of today to start working on this stuff. If you are a computer major, I highly encourage you to go a little further and program in MATLAB, program how to do our 3 elementary row operations. where you would take a row, do something with a row, add it to another row, replace that row. That's one operation. There's a row swap operation, and there is a multiply a row by a scalar operation. So I'll have some templates or some ideas for doing that, and then I'll pass that along. Yeah. Yeah. It won't be with the worksheet, but I'll post it something separate. And this can be done in MATLAB, but if you really want to extend yourself, you can go ahead and do it in, Java, C++, or Python or whatever you're into. Yeah. Let's say a week from today, midnight, a week from today. All right. So I have this linear combination statement. But it basically says what it says up there. So I'll go on and put it on our notes, but won't say much else. So equation AX equals B has a solution if and only if B is a linear combination of the columns of A. So that's essentially saying it's in the span. So saying something is a linear combination of a bunch of vectors is saying it's in the span of that bunch of vectors. So it's a linear combination of the columns of A, so it must be in the span of the columns of A. And the span of the columns of A will give it a special name later on. We'll call it col A, C-O-L. Okay, it's not so special, but that's what they call it. All right, so there's another theorem that comes up, a theorem of equivalences. And when you have these equivalency theorems, it's saying either one is true. If one is true, then everything's true, or if one is false, then everything's false. So it's all or nothing. Theorem 4. You have an n by n matrix. The following statements are logically equivalent. So what are the statements? It says here, for each b and Rm, the equation ax equals b has a solution. So if that's true, then these other three things are true. Each b and Rm is a linear combination of columns of A. That's what it says up above. Columns of A are in the span of Rm. I mentioned that already, and A has a pivot position in every single row. So it has a solution. We can even add another one here. What does it mean for a system to have a solution? What do we call that? It's what? Consistent. So you can say that your system is consistent. Okay, so you can check with the previous example that this in fact happened. We found a solution, so everything else is true. B is a linear combination of the columns, and the columns of A are in the span of Rm. In that case, it was R3. And then A has a pivot in every position. We saw the RREF, the reduced row echelon form, and we saw ones in each of those components, each of those rows. So it's all true. Okay, any questions? So this is the difficult part about linear algebra, is that it seems like it's like we're all working with systems of linear equations, which we are, but now we're translating this into this abstract idea called matrices and vectors. You can think of it as an abstract idea. You can you can try to get a handle on it, make it concrete for yourself by thinking that these are points or arrows in 2D or 3D. But when you go beyond 2 or 3 dimensions, then you can't picture it anymore. So it kind of gets lost in your visualization. But if you look at these as abstract ideas that have certain rules, and that's what math is really, a bunch of abstract ideas with certain rules that you need to follow. And if you follow those rules, then we're making connections to other things in math and hopefully out to real life situations. So in this case, we're making a connection between this abstract equation matrix equation AX equals B, and trying to bring that and connect that to a system of linear equations, our idea of a span, and the idea of a linear combination of things. Okay? Yes. Yes. If any one of these, actually, if any one of these is true, yeah, it's consistent. And if any one of these is not true, then everything else is false. All right. Looks like I have an example here. Yeah, Matt. Yes. Yes. That's also not here, but yeah, B is in the span of the columns of A. Actually, let's add those two things that we just mentioned. So this is the same thing as saying system is consistent. And what you just said, B is also in span. Oh, let's say span columns. Oh, that's what it says here. Never mind. Oh no, that's different. This is saying the columns of A are in the span of Rm, so that's different. So Rm, M remember is the number of rows, right? So the column of, yeah, this stuff will be hopefully clearer in, when we start talking about columns and column spaces. But this one was not said, Matt, what you said here is not listed in the list, but it is true because of B, because of this B, the criteria B, not the vector B. Okay, stop talking. It's confusing. Yeah, B and C are different. So columns of A, they span all of Rm, is saying that you take those columns and they would span the whole space. I guess to quickly talk about that here in this case, if you take a look at the columns of A here, that's a 1, -3, 0, and 2, -1, 5, and 1, 2, 3. If you take those three vectors, then they would span all of R3, which means you can get any linear combination. You can pick any point in R3, and then you can write these three vectors as a linear combination, or you can write that as a linear combination of those three vectors. Because it says in the theorem. I mean, what you're asking is how do you prove that, and I don't know if I can prove that off the top of my head. You can look in the book. I mean, they must have the proof for these things, and the proof goes, you know, in many directions. So they assume A, B, or D, and then they'll prove C. And then I think we could try to prove it, but I don't want to do it now. Yeah. So there is a proof of the theorem in the book. Um, and if you look through that, you might, you know, the idea of what it means for a column of A to span something might be something useful for you, or you might be able to get it from the proof. All right, I do have something here. This one says, let's do 15. Let's not do 16. All right, so in a 2 by 2 space over here, we're dealing with let A equal 2, -1, -6, 3, and B equal to B1, B2. Show that the equations A equals B does not have a solution for all possible B vectors, and describe the set of solutions, set of all B for which A and AX equals B does have a solution. So if we set this up like an augmented matrix thing and then solve for it using what we've been doing, which is RREF, then we should get some insight as to what's happening in this particular system. So we have 2, -1, and this is in 2D, so we might even be able to visualize it. So let's take a look at the augmented matrix. And let's do a row reduction move. I think 3 times R1 plus R2 will wipe out the -6 there. So that would be 6 minus 6 is 0. That would be -3 minus 3 is 0 again. And this will be 3B1 plus B2. So it looks like we have an interesting predicament here. If I did it correctly, did I do it correctly? Okay. So it looks like we have something interesting going on here. We got zeros here, right? Which is to say that for this thing to have a solution, then that means this third thing, the augmented portion of the second row, has to be equal to 0, right? If it's not equal to 0, then I will have 0 on the left-hand side is equal to something that's not equal to 0 on the right-hand side, and I would have no solutions there. So this would have a solution only if this equation is true. And it looks like we can pick a whole bunch of things for B1 and B2 here, right? As long as, let's say B2 is equal to -3B1, I'm going to get a solution. Like if I choose B1 is equal to 0, B2 is equal to 0, I have a solution. If I choose B1 is equal to 1 and B2 is equal to -3, I have a solution. So as long as this equation is true. So describe the set of all B's for which AX equals B has a solution. So you can say basically what we have written here, or we can formally write it. AX equals B has a solution if B equal to B1, B2, and B2 equals -3B1, or the original equation, 3B1 plus B2 is equal to 0. Okay, so let's see how it relates to the theorem. If in fact B1 was equal to or B2 is equal to negative 3B1, then all these things would be true. Okay? And otherwise, it would not. All right, let's squeeze in another theorem here. Is that it? That's a, yeah. Okay, we have an A is an M by N matrix, and then U and V are vectors in Rn, and we're assuming that C is a scalar. Then um, this is matrix and vector. So there's some sort of a distribution type of thing happening where the matrix can be distributed over two vectors. And there's some sort of associative property going on where if you have C times the vector, it's like multiplying by C times everything else. I don't know if that's that important, but it could come up later on when we're doing vector multiplication. Okay? Any questions? All right. I should show you is my assignment up here yet? You guys probably can't see the assignment yet. Okay, so here's your assignment, or this is what it's going to be. What's going to happen here is that it's going to walk you through, essentially what I want you to do is get familiar with MATLAB. So you're going to download either FreeMat or Octave, or if you have MATLAB, then that's great. Then you have MATLAB, then you can use that. Octave and FreeMat are very, very close to MATLAB in terms of what we're going to do. I think it'll work fine. But there are a few things that Octave, especially Octave, has that's slightly different in terms of writing programs in MATLAB. If you don't see yourself ever using MATLAB, but you're going to use Octave, then you can program the way they want you to program in Octave. Otherwise, if you want your Octave code to be readable by MATLAB, then you need to change a few things in Octave. But that's coding, and that's something we'll deal with later on. So what this walks you through is walks you through dealing with vectors and matrices with transposes and stuff like that. So there's several ways to input matrices and vectors, and I want you to get familiar with as many of them as you can, so that you can be able to deal with it. We have vector operations like scalar multiplication and addition. And so the vectors here are really, they transform into matrices, and so you're really dealing with everything here as a matrix. Element-wise operation is something a little tricky that we don't, when we do a matrix multiplication, we're going to do what's called, or we're going to do vector multiplication, we're going to do what's called a dot product. and we're going to call that the inner product. And so that's one type of product that we're going to be able to do from vector to vector. But when you're dealing with matrices, you have to adjust that vector to make it look like a specific type of matrix. Otherwise, your dot product might not turn out to be what it's supposed to be. So there's a few things here like the dot product and stuff that we haven't really discussed in detail, but you're going to be expected to walk through this and be able to do some of that. And this is the actual assignment. The actual assignment has 10 problems. The last couple of problems basically ask you to graph something, which probably won't do so much in this class. But it would be just good practice anyways if you're going to start to use MATLAB more. And then so what I want you to do is I want you to get the solutions for these things done in MATLAB. And I want you to essentially copy your screen, your MATLAB screen with the inputs and the outputs, and then paste that onto a document and then submit that. So that's what you're going to submit, and you're going to submit it online. The last one, since it is a graph, you actually have to take a picture of the graph and then just attach that to your document. Yeah. Yeah, I think we're going to change it to a regular document, just so we can see. All right. So as you're doing this and getting used to this, you should also take advantage of this and use it as a resource when you're doing your homework to check your work. So in an actual exam situation, you won't get to use MATLAB. You have to do things by hand. I mean, you can try to program in your calculator. If you do it yourself, that's great. If you have somebody else do it, then it's kind of like a waste. It's not you. But we'll talk about requirements for exam later. All right. Good luck with your work.